Hello, welcome back. Now we are ready to go to lecture 6 on this DFT course, and we are going to spend some time on an example of a functional to give you an idea on how we build a DFT functional. And this will be the Thomas-Fermi functional. So let me remind you what we've done so far in this DFT course. And in fact, the last lecture was all about the Hohenberg-Kohn theorems. So the Hohenberg-Kohn theorems are really the foundational theorems showing that DFT is a viable theory, essentially. And it proves that in DFT, you can write the total energy of the ground state, or actually the total energy of the system in general, in fact, as a functional of the density. So what it means, that this equation means, is that if you are given a potential V, a small v, you can write the energy as a functional of an universal function f, which is the kinetic energy and the electron-electron interaction, plus the energy corresponding to the potential v, and of course functional of n. So that's important because it means that we do not need to calculate any wave function, and usually those wave functions are very complicated because there are so many degrees of freedom, but we can use the density. And Hohenberg-Kohn theorem number 2 says that the ground state density, the ground state energy, is obtained by minimizing that functional E of n. So the minimization, of course, is using a variational-like principle, which correspond to finding the zero of the first derivative, first functional derivative of the energy with respect to the density. You will notice in this box that I also added a second term, the mu term, where mu is a Lagrange multiplier, and it allows me to make sure that the density that we are looking at are constrained to be normalized to the number of electrons. So that's very important. Now, what Hohenberg-Kohn theorems do not tell you is what that functional is. So in this lecture, I'm going to show you an example of an approximate functional. And then in the next lecture, we'll come up with a mechanism to build a more accurate family of functionals that will be based on the theory of Kohn and Cham. So let's go back to the original problem. This is the Hamiltonian we are trying to solve. Of course, this is an exact equation. We know the different ingredients there, the kinetic energy, the external potential, and the Coulombic interaction between the electrons. This is so nice. We know Hohenberg and Kohn establish that we can solve this problem for the ground state by writing the energy as a function of the density. But that's all that the theorems tell you. They do not tell you what the functional is. In fact, it's very complicated to find the exact functional. And in fact, there is no exact functional, at least as of today, that exists beyond one electron, I would say. And this is what it's all about. So today, in this lecture, I want to give you a sense of an approximation we can use to build such a functional. I mean, I'm going to tell you at this point that this functional is not great in terms of accuracy or predictability power, but at least it gives you an idea of the mechanism. And more importantly, and that's why I'm spending a screencast on this, it's going to show you the complexity in solving this problem. So we have three terms. Well, let's look at each of them one by one. I'm not going to do this in order. I'm going to start with the external potential. The reason why I'm looking at the external potential is because it's actually an easy one to write as a function of the density. So the energy can be obtained very simply by the equation in this box. We spent quite a bit of time looking at that. In fact, we've seen that even in the Hartree-Fock theory, we've seen this a number of times. Here, below the box, I'm just reminding you how we calculate the expectation value of the energy. And then with the second line, we see how this can be expressed as a function of the density. So I recommend that if you don't remember from a last lecture or the previous lecture, I recommend that you go back there where I described this. So that's good. 1/3 of the way, the energy corresponding to the external potential can be expressed exactly as a function of the density. Now, the second one that I'm going to look at is the Coulomb operator. In this case, the Coulomb operator, I mean here the electron-electron interaction. And one approximation we can use is this one in the blue box. This is something we've seen before in the Hartree-Fock description. This is essentially the interaction, the Coulombic interaction between electrons that are located at R and electrons that are located at R prime. So we integrate over the entire system because we have to essentially think a little bit of a little box that's of size d cube R or d cube R prime, and there's a certain number of electrons there, and they interact with all the other electrons. So this is really the Hartree energy that we have here. However, and this is important for you to realize this, we make a number of errors when we choose this. The first error we make is that we suppose that these are classical charges. So we are basically going back to what we learned in the introductory physics course in the Coulombic interaction, where we suppose the electrons are localized somewhere, and then we calculate this classical charge. Okay? So we will talk more about this, about the fact that we do not deal with classical charges. But even if we had classical charges, this equation is not exact, is not correct. And the reason why it's not correct is because we have a self-interaction term. So it goes like this. When we perform this calculation in the blue box, we are looking at the interaction between each of the boxes that I just described with every other boxes that I described in the system. Now, we do not know where the density at a given point comes from, but it can come from the electron itself. So basically what we are doing there in this equation, we also include interaction of the electron with itself, which is obviously not correct. The electron does not interact with itself through the Coulomb interaction, and yet this equation includes it. So this is also true, even if you did that for classical set of charges. I'm going to show that to you in a pretty convincing example in the next slide. But before I move on, I would like to tell you that we call this a mean field, the mean field approximation, because each electron interacts with the average distribution of all the other electrons, including itself. So we call it mean field, so that we do no longer look at the particular description of each electron. Okay, so let me explain to you, let me try to give you more sense about the self-interaction in the Coulomb operator. So we know the Coulomb operator is this one. I mean, you may wonder, if you are new to this field, which maybe you are, that such a simple-looking operator would give you so much headache. Well, it's a two-body operator, so that's the reason why it gives you so much headache. But this is exact. This operator is the exact one that we want to calculate the expectation value of. I attract your attention that here the sum only goes over the indices I that are larger than j. That allows me to not double count. So if an electron I interacts with an electron j, the electron j interacts with electron I, of course, but we only count that once, right? So that's why we have to only count the I larger than j. And it's also, of course, it's a strict inequality, because I equal j term, that would mean the electron interacting with itself would not work, and you would get all sort of trouble with the denominator. But in any case, we do not include that terms anyway, so let's not worry about that. This is the exact operator. Now imagine that you have a distribution of the classical distribution of charges. So we can write this with using the Dirac delta, And we suppose that we have a number of electrons that are indexed by the index I that are positioned at all the values Ri, for I going from 1 to n. So you can imagine that you have really point charges, the point charges being positioned at those Ri positions. Now that we have this, we can actually calculate this Hartree energy that I mentioned in the previous slide. So this approximation for the functional, for the Coulombic interaction, for the electron-electron. So we can calculate this. And we have all we need. And of course, you can already see, for all of you who are familiar with integration, we have the Dirac delta. So a lot of things are going to simplify, because integration of Dirac deltas always make things very simple. So let's do that. So the next slide. So the top box is what I just told you. And then I also remind you what's the density here for point charges. And we are just going to plug this in. So of course, we have NR and NR prime. So we have to include two sums and two Dirac delta, and we obtain something like this. You will notice in the front the sum of I and j, because we have n of r and n of r prime. So we have this, and of course the double integral simplifies tremendously because of the Dirac delta. So these are the charges that are here. So we obtain this term. It's pretty straightforward. Now you see that is slightly different from what we've seen before. There is a 1/2 term, there is a 1/2 in the front. And the sum over I and j, we sum over all the i's and all the j's. So the 1/2 is really to avoid a double counting, really. But look, if we now want to just go back to what I was using for the Coulombic interaction, I can also restrict the sum for I larger than I, for example, smaller than j, or I larger than j, whichever you want to use, which allows me to get rid of the 1/2. So if you have trouble with this, pause the screencast for 45 seconds and it will make sense to you. However, there is an extra term, which I call SI for self-interaction, because that sum there, the sum, not the last sum, but the previous one, includes I equal j. So even, so what does that mean? That means that if we use the approximation that's on the top of this screen, we see that even for classical charges, we do have self-interaction. And the self-interaction is embedded in this mean field approach. And of course, it's embedded there because we are looking at the interaction of everything with everything, including itself. All right. So the take-home message is that, yes, the functional on the top is a good approximation for the Coulombic interaction between electrons. But there are a number of problems. So the two problems that I mentioned to you is, first of all, is that it's considered pretty much the charges as classical. And second, it suffers from self-interaction. Okay? Now we have one more term to worry about in this, in trying to find a good approximation for the energy functional, is the kinetic term. So I like to really insist on this, that this is usually something that students do not consider as being a difficult problem, but it turns out the kinetic term is at least as difficult as the Coulombic interaction in terms of finding a functional of the density. I hope I can convince you with this, but I hope I will completely convince you in the next lecture anyway. But this is something that's important. It is not easy to find the kinetic term. So one historically important approximation was suppose that the electron's gas is homogeneous. So you could imagine that maybe that could be not too bad for a metal, certainly not for a molecule, but a homogeneous electron gas. The reason why we want to use the homogeneous electron gas is because we can actually find the kinetic energy for that exactly. And we will do this. But I'm going to first show you the result. I'm going to show you first the result here, which is the non-interacting homogeneous electron gas. If we imagine the density is of course homogeneous, so it's just the number of electron n divided by the volume, we find that kinetic energy functional is obtained from the density as obtained in the box, in the black box there. Now, you will notice that it's not a mistake. There is no square brackets here. I use the usual parentheses because n bar is really a number, right? It's because it's a constant in homogeneous electron gas. So this is a number that we can then use the usual function. I'm just saying this in case you think it's a typo. It is not. Now, the last equation on this slide is also important. It allows me to go a little bit further and to give you a form that's used more generally because we have n in front and we don't like the n, the number of electrons in front. So what we do, we multiply, and this is after the second equality, we multiply um, the integral of d cube r over v in front. And so this is of course equal to 1 because the integral of d cube r is the volume. If we divide by the volume, it's 1. So that's not much. But that allows me to show that we have n over v, and n over v, of course, is n bar. And therefore, my n bar 2 to the power 2/3 becomes an n bar to the power 5/3. And we have the integral. Now, you may wonder, why do I do this since n bar to the power 5/3 is a constant, right? It's a number. Well, it's because we are going to expand this result. We are going to generalize this result in just a second. Now, before we go there, I owe it to you to show you how we get this n to the power 5/3 for the homogeneous electron gas. So this is a little bit technical, but I think it's important because remember, all this is rooted in solid state physics and quantum mechanics. So it's important to understand these things. So let's just suppose that you have a homogeneous electron gas. So we have a Fermi sphere that's a true sphere with a radius kf in reciprocal space, which kf being the Fermi momentum, if you will. It's the momentum that corresponds to the Fermi level. So the kinetic energy for a particular momentum k is h bar square k square over 2m, the usual term in quantum mechanics. We can calculate the kinetic energy density, which will be the value Ts over the volume, right, to get the density. Now I replace the volume by L cube, and I wrote just the total kinetic energy is going to be the contribution from each k point. So I'm going to suppose that my k points are discretized in 3D. So we need 3, and this is ijk. And all this discretization, I have to calculate the kinetic energy of each of those boxes in reciprocal space. So those terms, of course, are h bar square over 2m times the k squared that correspond to that box. Now we have a factor of 2 in front because we can put 2 electrons in each boxes, one spin up and one spin down. All right? So this is the usual thing. So now we are going to try to calculate this. And if we suppose that kf is large enough, then actually, if we suppose that your box is large enough, really, it's more accurate. The discretization on Ks are very small boxes. So the Ks exist in a small box. So the distance between two different boxes is very small, basically. So the size of the box is small. And we can change the sum by an integral. And so that allows me to do an integral over a sphere. And of course, this is isotropic. So we end up with a 4 pi in front of that integral, which is basically the integration over the two angles, the two angles in spherical coordinates. And I end up with this integral that I have there, that I have on the screen. Then we solve everything and we find that the kinetic energy density is going to be obtained by the result in the red box. Now, I just want to tell you, and this is something I always insist a lot when I teach mathematical description to students. Everybody is going to understand this at different pace. It's okay. What matters is to understand it. It's very likely that you are wondering right now, how did he get this? Well, sorry. What happens here is that you have to pause the screencast and convince yourself. I gave you all the information, but it may take a minute to get there. it's okay. Your understanding of physics is not related to how fast you understand it. It's related to how well you understand it. You obtain this result. Now we can go a little bit further because, of course, we have Kf, and we would like to write this in terms of the density. So let me remind you that we also have this equation there. On the left-hand side, 4/3 pi Kf cube is the volume of the sphere of radius Kf. And on the right-hand side, of course, we put two electrons we put all the electrons in that sphere, and so essentially that corresponds to the number of electrons multiplied by the volume of each box, and the volume of each box is 2 pi over L cube. So these are the boxes that we have in a reciprocal space due to discretization of the fact that we have a big box of length L. And of course, the 2 comes again because we can put 2 electrons per boxes. So we need half as many boxes as we would need if we couldn't put 2 electrons in each boxes of 2 different spins. So that allows me for this equality will allow me to write Kf as a function of n and L. Now, what's nice about this, of course, is that you recognize n to the power 1/3 divided by L. So if I were to put this cubed, it would be n over L cube. N over L cube is the density. So you see, we can actually replace this by the density. And that allows me to write Kf as a function of the density to the power 1/3. Again, good place to stop the screencast to convince yourself. And then I can replace Kf in this equation. I just replaced just directly without any simplification. But after simplifying and remembering that n over L cube is the density, we obtain this result in the dashed red box, which is essentially the result that I used on the previous slide. So that's basically to show you that the kinetic energy density is going to be obtained by some factor multiplied by the density to the power 5/3. That's what I wanted to show to you that I used in the previous slide. So I think it's important to have seen this at least once to understand that the kinetic energy of a homogeneous electron gas goes up with the density with the power 5/3. Okay, good. So now let's go back to the kinetic term. And so what we do now, we do a big leap. We suppose that we do not have, of course, a homogeneous density, but we are going to write the kinetic energy in this form, just the same as I had 2 slides before, but instead of using the density of a homogeneous electron gas, just like this, I replace it by the actual density. And this is where the integral over the distance makes sense, over the volume makes sense. So this is basically the kinetic term. This is a very crude approximation for the kinetic energy, but at least it is expressed as a functional of the density. So you see, that's already nice, because now we have all terms all the terms. We have an approximation for each of the 3 terms as a functional of the density. Now this is basically what we have here for the kinetic energy. So one comment I can say is that you can always, the reason why you can hope it works is because you suppose that locally your system is homogeneous in each boxes. Basically, that's kind of the way to convince ourselves that maybe it's a good approximation. I'm not going to linger too much on this because it turns out this approximation is not great, but at least we can go through the gymnastics of showing that we can write the kinetic energy functional as a function of the density. Now we can put everything together. We have all the 3 terms. This is called the Thomas-Fermi model. And this is actually nice because we were able to write the Thomas-Fermi Hartree. We say Hartree because the last term, of course, is the Hartree energy. We were able to write a functional, energy functional of the density, where everything on the right only depends on the density, right? So that's a nice attempt. It's interesting from historical reasons. It's not great. In fact, if you look at the result here for argon, this Thomas-Fermi approach compared to the Hartree-Fock, for example, is pretty bad. I mean, we have you can look at the table there. The energy for Thomas-Fermi is really way far away from experiment. It's far away by about 100 atomic units, so it's almost like a 20% wrong. So that's not too good. I'm not going to spend too much time right now on the other approximations, but Hartree-Fock is doing much better. And in fact, all the other results are from DFT, and they do way better. Like the last one, for example, the GGA is almost exactly the experimental data. So so this is not very good because at the nucleus of the atom, the density is supposed to is computed to be infinite. Um, this Thomas-Fermi Hartree approach, there is no molecular system that's stable, so that's not good. So according to Thomas-Fermi Hartree, molecules do not exist, which is definitely not a very good sign of the validity of this approach. Um, we do not have any shell structures. You can see that in the plot of the density there on the right-hand side as a function of distance. There is no maxima in the density, so the maximum density would correspond to the shell. The density does not decay exponentially as it should, far away from far away from the nuclei. And so the total energy, as I said just a minute ago, is not great. So you can hope to improve this a little bit, and you actually already have the answer to that, because if you remember a few lectures ago, I actually showed you another functional for the single electron, and for that one we found, if you remember, it was called the von Weizsäcker kinetic energy functional, which is just given in the black box at the bottom of this slide. And that functional was exact for single electron. So of course, a single electron compared to homogeneous electron gas is basically the other side of the spectrum in terms of behavior. So one way to improve the Thomas-Fermi kinetic functional, which is suppose that the electrons are totally homogeneously distributed, we can add the von Weizsäcker functional. You will notice the coefficient lambda, which basically is a knob that you can turn to add more or less of von Weizsäcker kinetic energy. Now it's interesting because if you remember the Thomas-Fermi Hartree functional, it was a local functional because each of the term only depended on the density. No gradient, no first, second, third derivative, none of that. As you notice, the von Weizsäcker correction actually depends on the gradient. So essentially, the von Weizsäcker is a semi-local functional, and therefore this correction, the Thomas-Fermi von Weizsäcker model, is a semi-local approximation. It's very important to realize that it's very complicated to get a functional for the kinetic energy. And historically, there have been a lot of attempts to come up with functional, and it's actually still being developed right now. There is a very interesting literature about that, which is quite exciting. And who knows, with the development of machine learning, of big data, and so on, maybe people will go back to that. I don't know. But the possibility of improving upon the kinetic energy functional using this Thomas-Fermi approach is possible. Now, the Thomas-Fermi, there is also an expansion to the Thomas-Fermi Dirac model, because actually so far in this lecture I didn't talk about the exchange at all. We did not include the fact at all of the Pauli exclusion principle. Well, it turns out you can also improve that a little bit by including the exchange term coming from the homogeneous electron gas. I am not going to derive this equation here. It's obtained there. It's the exchange that can be obtained from a from a non-interacting homogeneous electron gas, you will notice two things. Um, that the density now, the power is 4/3. And then, of course, that term is negative because if you include the Pauli exclusion principle, you are, in fact, not allowing the electrons to get so close to each other as they would if you did not include it. And therefore, in, including the exchange will stabilize the system, right? Because the electrons are not as close to each other. And when they are close, they actually add energy because it's repulsion, right? Repulsion between electrons. There's a reason why we have a negative sign. So we can then use the density for prediction if we were able to solve all this. And this is what we'll do in the next lecture. So we could use DFT to predict the properties of material, at least if we have a better approach than the one we have here. So we usually obtain, when we are able to solve this problem more accurately, we can get the total energy, we can get its shape, its volume, the bond length, and we can then compare this to experiment and see if the approach is good. And if the approach is good, then it can be used for prediction. That's always what we want to do in theory. We don't want just to understand the experiment, which is also already great by itself, but we want also to be able to make predictions. So another big development that have been going on over the past 10 years, and it's still very much alive, is to this design of new materials. So if you have a theory that's accurate enough, you'd be able to design new materials. Now, one big caveat is to get good functionals. We always say DFT, saying I'm doing DFT without saying which functional you use is meaningless. Um, so good functional can actually allow you to get a number of properties. And as you become more familiar with DFT and being a practitioner of DFT, you will get the sense and the knowledge of which functional works best for different classes of system and classes of problem that you are trying to solve. Um, so what I should say, and just to make sure there is no misunderstanding, the functional I described in this particular screencast is not great. It's great for pedagogical reasons, is great for historical reasons, but in terms of prediction, it's pretty bad, I would say. It's pretty bad. And the reason why, and this is what I'm going to end with, the reason why it's pretty bad is because we made two very crude approximations. The approximations are as follows. The first one is the kinetic energy part, which we use the homogeneous electron gas, which is, of course, pretty far from what a real material is. And of course, the second one is the Coulomb energy. Remember, we are using the Hartree energy functional, and we highlighted the fact that it's only for classical charges, but even so, for classical charges, we have what's called a self-interaction problem. So these functionals we use are not great. So historically, that was an issue because when people came up with this idea of DFT and this discussion, just like I discussed now, it turns out that Hartree and Hartree-Fock is actually much better than what I described today in this screencast. And it made people reluctant to use DFT initially. They said, yes, I understand it. I get it that it may be a wonderful thing to do, but this is not accurate enough. Yes, maybe Hartree-Fock is suffering from the lack of correlation, but we are missing so much more when we use this Thomas-Fermi-like functional. The good news is there have been a very important development over the past 20, 30 years for functionals, which made it possible now to describe more and more accurately the materials, I would say beyond Hartree-Fock. I mean, the Hartree-Fock is not used much anymore, certainly not in solid state or material science, but it's because of the development of functionals. And it's all hinges on what's called the Kohn-Sham theorems. And the Coulomb theorems is what's coming next. So that will be the next screencast. and it will really open the door to systematic improvement of functionals and basically where the field is today. So thank you very much for following this screencast. Thank you.